Okay, welcome to today's chat. We're going to be talking about the Earth in the first half of the chat and then talking about the Moon. Using a new type of board, so I'm going to see how this electronic pen works. So if there are a few trouble spots, you'll just have to bear with me on this one. Okay, we start with the Earth when we're talking about the planets because we're most familiar with the Earth. We know the Earth very well because obviously we live on the Earth. And we're going to use the Earth as a sort of benchmark to compare all the other planets to. You know, when we're talking about distance from the Sun, it's based on the astronomical unit, the distance, the average distance from the Sun and the Earth. When we talk about mass, we talk about, how many times is a planet times the mass of the Earth. So, again, familiarity is going to allow us to, discuss the Earth and then compare the other planets to it. Okay, so let's get started. First of all, the Earth is the third closest planet to the Sun. Mercury and Venus orbit within the Earth. All the other planets orbit outside. And again, the average distance from the Sun is 1 astronomical unit. Again, this unit, the astronomical unit, is actually based on the distance between the Earth and the Sun, and really the average radius of the Earth's orbit. And of course, we know that it takes the Earth to orbit the Sun in 1 year, 365.25 days approximately. And again, we'll talk about all the other orbital periods of the planets based on that. So, what's special about the Earth? Well, one of the interesting things about the Earth, of all the terrestrial planets, is the Earth has a pretty good-sized moon. Yes, in terms of the 4 inner planets, Mercury, Venus, Earth, and Mars. Mars does have 2 moons, but they're basically just captured asteroids. They're really small. If we talked about the fractional mass of these asteroids compared to Mars itself, and these moons of Phobos and Deimos, it really would be a very small number. However, the moon represents about 27% of the radius of the Earth. The size is 27% of the Earth, along the radius or diameter. But because the volume of a planet, planets are fairly spherical, goes by the cube of the radius, that 27% radius, really leads to a much lower mass. And the moon is only about 1.2% of the mass of the Earth. So it would take about 80 moons to equal 1 Earth. Again, we discussed the orbit. The radius of the orbit is measured in terms of astronomical units. The astronomical unit is 1.5 times 10 to the 8 kilometers. So, whenever we talk about distances, if we multiply this number by the number of astronomical units, we can convert that to kilometers. Again, the orbital period, the time it takes to go around the Sun once, is 365.2526 days, depending on how you round it up. And the 25 results in a leap year, the 0.25. And the fact that it's a little more than 0.25, once in a while we have to adjust for a leap second. We're really going around the Sun at a very high rate of speed. 30 kilometers per second is 67,000 miles per hour. And just to give a comparison, we're going nearly 100 times faster than the speed of sound in our orbit. But because we're so massive and the size of the orbit is so big, we really can't feel this motion. The eccentricity of the Earth's orbit is 0.0167. And eccentricity tells you how oval the orbit is. So we go around the Sun in a fairly circular orbit. And what this means is that as we're going around the Sun, our distance doesn't change very much. So really, the position that we are with respect to the Sun and the solar system has very little to do with the temperature changes that we experience in the season. Those are really more a function of the Earth's axis. The fact that we have an axial tilt of 23.5 degrees leads to the seasonal changes. Now, currently, the way the axis is pointed. It's pointed toward the North Star, or the star Polaris, and that's the reason why Polaris never moves. Because our axis is aligned with that, it's going to stay in the same position in the sky. Now, the axis does change over a very long period of time. Currently, it's pointing at Polaris. But if you were to come back to the Earth in many, many years, say in about 12,000 years, you would see that Vega, a very bright star in the sky, would be our new North Star. And this process is called precession. The axis of the Earth actually goes around in a circle, and every 26,000 years it repeats itself. Now, in the shorter period, the axial tilt again is responsible for the seasons. We live in the northern hemisphere, so when the axis is tilting toward the sun, we experience more daylight, and we experience a more direct sunlight on the Earth. We're now going into autumn, depending on where we are in the semester, and eventually the axis tilts away from the sun, and this leads to shorter days, so there's less surface heating and less direct sunlight. What's interesting is we are furthest from the sun during the northern summer, and we are closest to the sun during the northern winter. Okay? Again, the Earth's axis, or I should say the Earth's orbit, is not entirely round. There's a slight deviation. And this leads us to get closer to the sun during wintertime, perihelion, and further from the sun during aphelion. But it's the axial tilt that has a much greater effect on the Earth's weather, and therefore the seasons are really dominated by the axial tilt. And again, here's another diagram. We can see what the Earth looks like, and this is exaggerated. The Earth obviously is not that close to the sun or that large compared to the sun. But here you can see that during the northern summer, that we have the southern winter, and clearly with the axis tilted toward the sun, you're getting a lot more light up there for a longer period of time. In the meantime, the bottom axis has to be pointing away if the northern axis is pointing toward, resulting in less illumination. So, when we talk about the other planets, we will talk a little bit about their axial tilts and whether or not they experience seasons. We'll see some planets like Mercury, which has almost no tilt at all. Therefore, it doesn't experience seasons. Jupiter is more or less the same way. It has very, very little axial tilt. But planets like Mars and Saturn have a similar axial tilt to us and do experience seasons. The extreme case is Uranus, which is tilted at 90 degrees. So it has the most extreme seasons of all the planets. In terms of atmosphere, the atmosphere on Earth is pretty unique. And it's unique in terms of composition, and the composition is a result of some biogenic influence. There's a very strong coupling between our atmosphere and the oceans. The Earth probably started out with an atmosphere dominated by carbon dioxide, but much of this carbon dioxide was taken up by the ocean to form carbonate rocks, and photosynthesis took the rest of the carbon dioxide, or most of the rest of the carbon dioxide, out of the atmosphere, so at a much lower rate today. But again, most of what we call air is nitrogen. About 3/4 of all the air you breathe is nitrogen. We, of course, would suffocate without the oxygen, which makes up a little less than 1/4. And then if we count all the other gases, argon is an inert gas, makes up a little more than 1%. Water vapor is sort of interesting in this discussion because depending on where you are, you can have smaller amounts of water vapor in the air, more water vapor in the air, and it even depends on the weather. At our location during the summertime, there's a much higher water content because the air is much warmer. It can hold more water. During the winter, it actually gets quite dry, and the water content can drop off. Now, this very wide variation in water vapor also reflects different climates. If you go down to Antarctica, even though the South Pole is covered with a tremendous amount of snow, it's one of the driest places on Earth due to the very cold temperatures. The air just can't hold a lot of water at cold temperatures. Higher percentages, up to 1.7%, you would generally see in the tropics near the ocean. And again, other trace gases include carbon dioxide. There's not much carbon dioxide in the Earth's atmosphere, certainly not compared to what we see on Venus and Mars. However, that little bit of carbon dioxide, that 0.05% carbon dioxide, has a tremendous effect on the Earth's climate. Slight variations in this trace gas have very big implications as to what happens. In this year, 2012, we experienced the greatest amount of sea ice melting in the Arctic Ocean, and we have fairly good evidence that this is due primarily to the carbon dioxide emissions from industry. Let's talk about parts of the atmosphere. We're most familiar with the lowest layer of the atmosphere called the troposphere, and the reason for this is because we live in the troposphere. This is where most weather occurs. We experience the greatest amount of mixing due to convection. Again, almost all weather is in the troposphere. And the troposphere, even though it's one of the thinnest layers of the atmosphere, accounts for about 80% of the total mass of the atmosphere. If you can get above the troposphere, you've basically gotten above 80%, or let's convert that. You've gotten above about 4/5 of the total atmosphere. Trying to do math in my head while I'm talking is difficult. So again, we're talking about weather. Troposphere contains almost all the planet's water vapor, and troposphere is where the atmosphere interacts with the hydrosphere, the oceans, the seas, the lakes, whatever. Water vapor from the surface, as it evaporates, is then pushed high into the upper atmosphere where it condenses and forms clouds. In fact, when we look at storms, most storms are powered not just by temperature differences between different air masses. They're powered by a lot of the heat released as water vapor condenses to form clouds. In fact, tropical cyclones, such as hurricanes, are some of the most powerful storms on the Earth, and they get almost all of their energy from the latent heat provided by the ocean. We have convection cells. The two at the equator are known as Hadley cells, and these basically are due to air warming at the surface and then cooling up in the upper part of the troposphere and then sinking again. Without the Earth spinning, we'd only have one convection cell in the northern hemisphere and one in the southern hemisphere, but we actually get 3 cells as a result of the spin. The Coriolis effect creates this. And you can see some of the convergence at the equator where you have warm, moist air rising, and then you can see, although it varies depending on the weather patterns, the air sinking again at mid-latitudes. Weather movement is controlled quite a bit by these convection cells. Oscillations between the convection cells can create strong weather fronts, but the boundaries generally depend on your latitude. So I shouldn't say the boundaries. The movement of the weather depends on your latitude, is strongly influenced by your latitude. In most of the United States, in the lower 48, most of the weather goes from west to east. If we go south of the lower 48 states, we generally start having the weather going the opposite direction. So again, our atmosphere, dominated by nitrogen, a significant fraction of oxygen. And then the trace gases, especially the greenhouse gases, do affect climate. Weather is generally powered by heat from the sun heating either the ocean or the surface of land, and then that heat being transferred to the atmosphere, transferred in terms of energy to the atmosphere in the form of latent heat. Above our troposphere, and again, about 80% of all the mass of our atmosphere is down here, we have another layer, a very important layer, called the stratosphere. And the reason why the stratosphere is so important to life is because of a small layer which exists within the stratosphere called the ozone layer. And this is dominated by triatomic oxygen. Normally oxygen, when it forms molecules, two oxygen molecules bond together. But in some cases, especially when exposed to electrical discharges or ultraviolet light, ozone, a third oxygen, can bind to this. And again, ozone is very important to life because ozone has the ability to absorb ultraviolet light very efficiently. Now, until the ozone layer formed on the Earth, no life could exist on land because ultraviolet light just destroys most living tissue. However, with the ozone layer, we have a nice shield. It doesn't allow us to see the ultraviolet part of the spectrum when we're looking up into the sky, but it does shield us from this harmful energy. Above the stratosphere is a mesosphere. Here the temperature actually begins to drop. There's really not much in terms of air molecules up here. And, temperatures up here get very cold, but the atmosphere is really so low in density that, you wouldn't be able to live for very long above the troposphere. And, even the stratosphere would have a very low density. In the mesosphere, it almost seemed like we're in space due to the low densities. Above the mesosphere is the thermosphere. Sometimes we call this the ionosphere. At these altitudes, a significant portion of the atmosphere is actually ionized. And it's highly susceptible to solar wind because the magnetic field of the Earth interacts with the solar wind. As the solar wind increases, it dumps more charged particles into our magnetic field. These particles trapped in the magnetic field can then make it down to the atmosphere where they interact again with the mesosphere. And the ionosphere actually extends up to the thermosphere. Here's where electrons from the solar wind flow into the magnetic field of the Earth directly, and this is where we see auroras. Most meteors that we see during a meteor shower are actually vaporized up in this upper level. And the thermosphere, in fact, is so low in density that it breaks into different compositions. It stratifies. The lowest part of the thermosphere is dominated by nitrogen gas. Go a little bit higher and slightly lighter than nitrogen, oxygen sort of dominates. Above that, we have helium, and this helium gas doesn't stay in the atmosphere very long. It's given off primarily by different cracks in the Earth. Nuclear decay within the Earth actually generates this helium. And then at the very top of the thermosphere, we have a higher ratio of hydrogen, being the lightest of all gases. This is probably mostly liberated by photoionization, dissociation of water molecules. Now, oftentimes we hear the term greenhouse effect, and it typically has a negative connotation. In fact, the greenhouse effect is a very important thermoregulator for our climate. And without the greenhouse effect, our Earth would basically become a big snowball. Temperatures at the Earth are warmer than they would be without a greenhouse effect, because the greenhouse effect can trap energy from the sun. It's like putting a blanket or a coat on the sun. It slows the amount of energy that can escape into space. Now, the way the greenhouse effect works is it works like a greenhouse. Glass in a greenhouse allows visible light to make it to the surface. Okay? And that's exactly what we have right here. We have the visible light making it to the surface of the Earth and heating up the surface. This generates the weather, this powers the weather, whatever. Now, as the surface gets warm, it radiates because it's a black body. It tries to radiate infrared light. And this infrared light, without the atmosphere, would simply just escape out into space. However, with the presence of greenhouse gases, a large amount of this is scattered around and just slows down the rate that energy can escape, and therefore keeps the Earth much warmer than it would be otherwise. So the greenhouse effect has been around for a very long time. It's a positive thing. It's kept Earth warm enough for life to really thrive. What's not good is the accelerated greenhouse effect due to the emissions of carbon dioxide. And again, without the greenhouse effect, the mean surface temperature of the Earth would be well below the freezing point of water. Most of the oceans would freeze, if not all the oceans. But as we burn more and more greenhouse gases, we increase the amount of heat retention. Basically, we keep the amount of heat that is in the Earth or on the Earth's surface. Global temperatures go up, and what's happening is, because we're emitting so much carbon dioxide, we're raising global temperatures very quickly. It's not really the amount that we're raising temperatures. Okay? The Earth has actually been much warmer at different points in history. Okay? There's actually been much more carbon dioxide than we can actually release into the atmosphere. What is so dangerous about this is the rate at which it's happening. Usually it'll happen over very long periods of time. Temperature changes due to changes in the atmosphere. In fact, we believe one of the greatest extinction events on Earth was caused by a rapid change in temperatures due to a very large release of carbon dioxide. We're sort of doing the same thing. We're rapidly increasing temperatures by increasing the amount of carbon dioxide in the atmosphere. Where did the Earth's atmosphere come from? Well, during our discussion of the formation of planets, we said a little bit about the fact that the terrestrial planets were in a part of the solar system that was really too warm for volatiles to exist. Volatiles are anything that will either boil away or be liquid at fairly low temperatures. So ice is a volatile, methane is a volatile, gases are volatiles. So if volatiles couldn't initially condense in the inner solar system, where did they come from? Well, basically what happened is small amounts of volatiles did attach to some of the planetesimals as they formed. They were chemically bound. When the planets came together, these volatiles were trapped within the planets. And eventually the planets became large enough in size to actually have enough gravity to hold on to these volatiles. So, during the Earth's formation, it wasn't that it captured these gases from the solar nebula, like Jupiter did, like Saturn did, like Uranus and Neptune did. The atmospheres basically came from, mainly volcanic emissions, that as these materials bubbled to the surface, as magma became lava and made it to the surface, it released these gases into the atmosphere. Now, the primitive atmosphere that the Earth had, was composed of methane, a lot of water vapor, carbon dioxide, and a small amount of nitrogen. Most of the methane was converted into carbon dioxide by ultraviolet light. Eventually, the carbon dioxide was incorporated into carbonate rocks, and we have our oceans to thank us for that. In terms of the water vapor, most of the water vapor actually condensed, rained onto the surface, and filled up the oceans that we have today. And of course, carbon dioxide was also given off in the form of CO2, and again, that was incorporated into rocks to create carbonate rocks. So initially, if we looked at the primitive atmosphere, we'd see methane, we'd see water vapor, we'd see carbon dioxide. Again, the first three, really were, absorbed or transformed and lost. So the small amount of nitrogen that we had left forms the basis for most of our atmosphere today. A small amount of carbon dioxide was converted into oxygen by cyanobacteria and other primitive photosynthesis organisms. And here's sort of a chart that traces different atmospheric composition. We can see very early on that the carbon dioxide started at a fairly high level, but then decreased with time as it was incorporated into the oceans and converted into oxygen by photosynthesis. Again, most of the loss of the carbon dioxide actually occurs through absorption in the ocean. And it wasn't until much later on that the carbon dioxide was converted into oxygen by photosynthesis. We look at the surface of the Earth. Most of it's covered with water. This is basically the water that was initially in the atmosphere as water vapor. As the temperature of the Earth cooled down, this water vapor was converted into clouds, which rained, and of course, most of the surface is now covered with this. We do have large ice caps at the poles, primarily at the location of Antarctica, but also in Greenland. The ice pack that we have over the North Pole really isn't very thick, whereas the Antarctic ice cap and the Greenland ice cap is actually miles thick. We are the only planet surface known to have life. We are the only terrestrial planet that has tectonic activity. And plate tectonics has been a very strong force in terms of changing not only the topography of the Earth, but the basic geology of the Earth. One of the most important features that we have on the surface of the Earth are the oceans. And the oceans play a very critical role in terms of managing the heat of the Earth. It has a strong coupling to the atmosphere, so therefore there's quite a bit of heat exchange that occurs. Water, because of its very large specific heat capacity, allows the oceans to absorb a tremendous amount of heat during warmer times and allows it to release this during colder times. A very good example of the influence that the oceans have in terms of transporting heat energy from one place to another is the Gulf Stream. And here we can see the Gulf Stream as it winds its way along the coast of the United States, taking some of the heat from the lower latitudes and making Europe much warmer than it should be. Ocean currents are a very important mechanism for transferring heat from one location to another. In this chart right here, you can see the Gulf Stream. It's part of a much larger thermohaline circulation system that transports heat from different locations. And these currents are not just powered by general thermal convection. They're also powered somewhat by the change in salinity that happens as the water changes location. So the Earth is really the only one with liquid water on its surface of all the planets. So really be hard to compare the properties of our oceans to any other planets out there. But some moons are thought to have subterranean oceans. Another very unique feature of the Earth is its crust. It really has some of the most distinctive or greatest dichotomy in the crust, in that some of the crust is very thick and old, is known as continental crust, and some of the crust is rather young and very thin. The continental crust is typically made of lighter silicate rock. Because it's lighter, it's more buoyant, it floats higher on the mantle, whereas the ocean crust is heavy, usually more basaltic rock, and tends to sink, and therefore is constantly being renewed. Again, as far as plate tectonics go, it's a feature on the Earth that is unique at this current time. We think that both Venus and Mars probably had active plate tectonics, but those have since ceased. Venus might still have some mountain building mechanisms that are powered by convection within the mantle of the planet, but it's not true plate tectonics like we see here on Earth. Plate tectonics is basically powered by heat being released from the core, heating up the mantle. The mantle rises due to greater buoyancy. This material then spreads out and pulls on the lithosphere, which is the solid part of the Earth's outer layer. The lithosphere actually includes part of the upper mantle and the crust itself. And this lithosphere is really what's moving, and in some cases coming together to form converging plate boundaries. Here's where we see mountain building. As the two plates converge, the oceanic crust, being thinner and denser, tends to sink below the continental crust. And as the two converge together, the continental crust becomes warped, and it also experiences a lot of volcanism. One of the common geological features that we see on the Earth are composite or stratovolcanoes. These are very common from material which is melted at these converging plate boundaries and then bubbles up to the surface. To the best knowledge, stratovolcanoes are sort of unique to the Earth in this form, because we do have some similar features on other planets, but really, it's really a feature that we see mainly on the Earth because of the existence of plate tectonics. Diverging plate boundaries lead to mid-ocean ridges, and this is where the crust is literally being ripped apart, and it's almost always oceanic crust which is being formed at these locations. That's why the ocean crust is so young. And where the mantle tends to be rising toward the surface, we tend to get these diverging plate boundaries. And if we look at this map right here, it shows the Earth, and it shows regions where the ocean crust is actually ripping apart. Here's one diverging plate boundary, which is currently moving North America and South America away from Europe and Africa. Another diverging plate boundary can be found in the Pacific. The colors show red as being much younger crust, and progressively going from red to orange to yellow to green to blue, blue being the oldest. Notice that all the continents are gray. The reason for this is the continental crust is significantly older than the oceanic crust. Looking at the interior of the Earth, the interior of the Earth shows a general structure for any of the terrestrial planets. The difference may be that the Earth has a slightly larger outer core than any of the other planets. And the inner core is made of metal. It's solid. The outer core is much larger in volume and is thought to be liquid. Now, for the other planets, their cores are also made out of metal. However, it's thought that these cores are almost entirely solid or only have a small region which is liquid. Why is this so? Well, mainly because Earth is the largest of the planets, and therefore at higher temperatures, its core temperature being greater, is going to be more liquid than the other ones. Above the core, of course, we have the mantle. The mantle is dominated by magnesium and iron silicates, magnesium and iron oxides, very heavy, rocky material, which is much denser than the stuff that we find on the surface. In the crust, we have rock that's dominated by a lot of basalt and granite, rock that's lighter than the mantle material. Again, looking at the composition, the upper mantle, olivine, pyroxene, garnet. These are the minerals that we tend to find at this level. Olivine is iron and magnesium silicate. Pyroxene has a different chemical structure, but is of similar made of similar atoms. Garnet includes, I think, aluminum, but I'm not a geological expert here. At much lower layers, we tend to get iron and magnesium oxides. At high temperature and pressure, these become perovskites, which have sort of a cubic structure to them. And again, the core is very important, when talking about the Earth and the magnetic field. Our magnetic field really protects our atmosphere from solar wind, and our atmosphere in turn protects us from radiation from space. So without the existence of the magnetic field, our atmosphere would be greatly altered, and again would make life very difficult to exist, especially on land. Again, the solid core at the center is where temperatures are the highest. It's solid only because it's under a tremendous amount of pressure. It's actually as hot as the surface of the sun, or maybe even a little bit hotter. But at these depths where there's so much rock pushing down on it, it takes a solid phase. The liquid outer core, which is made out of mostly iron, probably some nickel, and some other things, is what's responsible for our magnetic field. We have convection within this, which creates eddies. Actually, differential rotation and convection within this creates eddies, and this leads to generating electric currents, which in turn induce magnetic fields. Interestingly, the Earth's magnetic field changes its polarity. It flips. Approximately every quarter of a million years. It's somewhere between being periodic and random. We haven't had a reversal in quite a long time, so we're not near the average. It's been about 790,000 years since the last reversal. However, current measurements do indicate that the Earth's field is weakening and approaching another reversal. But since this process takes such a long period of time, we don't expect this to happen anytime soon or complete its reversal anytime soon. It's not that the magnetic field disappears when it reverses. It actually becomes somewhat chaotic. But this can lead to stronger auroral activity and interaction with the particles in the upper atmosphere. The magnetic field, which protects us from radiation, or at least protects our atmosphere from radiation, actually traps protons and electrons in regions we call radiation belts. And these are known as the Van Allen radiation belts. There's an inner and an outer belt because the most common particles that are trapped include electrons and protons. We generally find more electrons in the inner belt and more protons in the outer belt. Now again, solar wind does not make it to our atmosphere directly. If it did, it would really disrupt our atmosphere and probably result in the destruction of the ozone layer. However, some of the radiation that does get trapped in the magnetic field can be sent toward the poles, causing them to collide with the upper atmosphere. And this creates a very beautiful phenomenon known as an aurora. When we have a very intense solar storm, when the sun sends off a very large cloud of magnetized plasma at the Earth's magnetic field, it can squeeze the magnetic field and really send a larger number of particles out of the field, allowing the aurora to be observed at very at much lower latitudes, like our own location. Usually, if you want to see the aurora, you really have to go up near the Arctic Circle. But again, during intense storms, the number of particles that make it down the magnetic field lines to the Earth greatly increase, and the magnetic field lines become distorted. So once in a while, we do see auroras as far south as this location. And again, here's sort of a schematic of what happens. We can imagine electrons being squeezed out of the Earth's magnetic field. And as that happens, they make their way down to the North Pole and the South Pole. And as they collide with the molecules in the upper atmosphere, they cause them to fluoresce. Just like when you send electricity through a fluorescent bulb, it causes the mercury in them to glow. Sending electricity or electrons through the upper atmosphere causes them to glow. Here is an actual image of the ultraviolet light being emitted by these fluorescing atoms during one of these solar storms. Okay, well that's the Earth. And again, we're going to sort of use the Earth as the standard for comparing to a lot of the other planets. That's really the most useful thing to do in this course. If we want to understand another planet, compare it to something that we know. And the Earth we know pretty well. Now, in this chapter, not only are we talking about the Earth, but we're also going to talk about the Moon. And since we've gone over the Earth, it's very convenient now to just segue right into the Moon and compare the Moon to the Earth. The Moon is the only major moon for any of the terrestrial planets, as we discussed before. It's about 27% of the Earth's radius. And although it's only 1/80th of the Earth's mass, it is pretty large compared to the planet. Okay? It's very unusual that you would have a moon. In fact, the Earth's moon is the only moon which has at least 1% of the planet that it orbits mass. Our moon is not the biggest moon. Ganymede's bigger. That's the largest moon that orbits Jupiter. I think Callisto's bigger too. That's another moon of Jupiter. Titan is bigger, but both Jupiter and Saturn are, over 300 or 100 times bigger than the Earth in mass, respectively. The Moon has no atmosphere, so it will range in surface temperature from negative 170 degrees all the way up to 130 degrees centigrade, and it's much lower in density than the Earth. We only see one face of the Moon. The Moon only keeps one side turned to us at all times. It rotates once every orbit, so we can never see the backside of the Moon, or what we call the far side. This gravitational resonance, this gravitational locking, is caused by tides. Because the Moon orbits very close to us, the tidal interaction between the Earth and the Moon has slowed down the rotation to one rotation every orbit. And this is very common for bodies that orbit very close to one another, that you get this gravitational resonance. And again, we never see the far side. The far side of the moon was really not ever seen until the advent of space probes. And the interesting thing is when we see a lot of mares or seas on the near side of the moon, those are those dark patches on the moon. But on the far side, you've got a few small ones, but primarily it's covered with mostly highlands. The surface of the moon is very old. The surface basically is over 4 billion years old because that's about the age of the moon. It hasn't changed very much. Other than cratering due to the Great Bombardment and mares when the lava flooded in there, not a whole lot has happened since it's formed. In fact, its surface is covered with something called regolith, which is dust from the constant impacts from space. The moon has no atmosphere to protect it from even the smallest micrometeorites, and therefore the surface is constantly being ground down by this. Compared to the Earth, again, the moon is very old in terms of the rock we find on the moon. On Earth, most of the original rock has been destroyed through plate tectonics. Now, the moon is the only celestial body that we've ever visited in person. We initially sent many robotic missions to it. The Luna and Surveyor missions were the first to land on the moon. They were followed by the Apollo missions, which actually brought samples back to the Earth. And you can see the different locations for these missions. The red represents the Luna missions. The green represents the Surveyor missions, and then the yellow represents all of the Apollo missions. You can see the different Apollo missions. Most of these Apollo missions happened in relatively flat areas. The reason for this is they needed a safe landing site. One did actually land in the highlands, but landed in the base of a crater, which had been smoothed out by lava flooding. Again, if you were to step on the surface of the moon, you'd notice that the composition of the soil was pretty much like talcum powder. Again, microscopic impacts are constantly grinding down the rock, producing this very fine powder. Like the Earth, we can divide the surface into two different types of terrain. On the Earth, with continental and oceanic crust, the oceanic crust being the lower elevation regions, which are filled in with water. In this colorized view of the moon, we can see the highlands shown in mostly yellow, and the lowlands shown mostly in blue. Now, on Earth, the lowest regions are occupied by, again, the oceanic crust, which then became flooded with water. On the moon, the lowlands were created by massive impacts. You can see that, when we're looking at a lot of these different features, they have a nearly circular shape. So one impact created that one. One impact created this one. They're very circular, and even the largest ones can be basically broken into circular impacts. If you hit a planet or a moon with a very large impactor, you carve out a lot of material. The material is going to try to fill in these lowlands, and that's exactly what the moon did billions of years ago. The lunar highlands are the oldest part of the surface. These were not filled in with magma by any, on any large scale. These regions again are heavily cratered. They go back to the age of bombardment. These rocks are made of breccias and anorthosites. The breccias, basically, as the name implies, are just broken rocks cemented back together. The anorthosites are very light rock that is, I guess, similar to some of the continental crust in some respects in its low density on Earth. The lunar mares are primarily filled with basalt, similar in composition to our own oceanic crusts. And they're much younger than the highlands. And again, these are regions which have been filled in with lava. Here you see a rill that's actually a channel of lava that probably flowed at one time on the surface. You know, even the mares, which appear to be smooth to our eye, have a lot of different craters on them. And again, the breccias and the anorthosites are the ones that we generally find on the highlands. The anorthosites have large amounts of feldspar, just like the granite in the continental crust has a large amount of feldspar. The breccias, the anorthosites, tend to be very light in color, lower in density. The lunar mares are dark because they're filled with basically darker rock. And again, this is the basalt. It's a heavy, dark-colored volcanic rock that dominates the ocean crust here on Earth and dominates the mares on the Moon. The craters that we see on the Moon probably once dotted the Earth's own surface. But between plate tectonics and erosion, almost all of these craters have been removed. We still see some examples of meteor impacts, such as the crater out in Winslow, Arizona, and in some other places. There's some very famous craters. There's one in Quebec, up in Canada. There's one in Australia. But we don't have anywhere near the number of craters on the Earth that we see on the Moon. The Moon is dominated by these craters. And the way that they form is very simple. Some type of impactor. It can be a piece of asteroid. It can be a piece of comet. It can be as small as a grain of dust. It can be as large as several miles across. When this comes in, it's coming at a very high speed and with a tremendous amount of kinetic energy. In fact, it comes in with so much energy, it basically vaporizes on impact. Okay? It creates a huge fireball, and as this fireball expands, it carves out the material, creating sort of a bowl-shaped structure. And that is exactly what we see with the craters. If we look at the smallest craters, they are almost perfect bowls. But as the craters become larger and larger, the energies become larger, and elastic rebound will actually cause the center of some of these craters to produce a peak. And in other cases, so much energy can be released that lava can fill in the floors and create a flat surface. You can actually tell the age of some of the larger craters. This is the crater Copernicus, by the rays that surround the crater. Very young craters still have these structures called rays, and the rays are just simply material that's been ejected out of the impact. Over time, smaller impacts erase these rays, and all you have left is the crater itself. Look at the bottom of Copernicus, however. You see here's the crater wall, and it's not a nice bowl. The bottom of this crater is pretty much flat. And that's because, once again, magma came in and filled in this bowl to pretty much only leave the crater walls behind. The Moon is much less dense than the Earth. As we'll discuss in a little bit, we believe that the Moon was actually composed of materials blasted from the Earth's mantle. So inside the Moon, it didn't differentiate very much. It was pretty much a homogeneous material. The lighter material did make it to the surface, forming this light crust. the moon's interior is dominated almost entirely by a large mantle. And then there's thought to be a small core, but this core isn't as dense as what you see on the Earth and may not be as pure. The Earth's core is thought to be primarily composed of iron and nickel. Again, we believe that the moon formed when a large Mars-sized planetesimal crashed into the Earth. This theory is pretty well accepted, and what probably happened is the Earth wasn't alone in its orbit. It probably formed with another large protoplanet at one of its Lagrangian points. This wasn't very big again. It was about 1/10 of the mass of the Earth. But during their collision, it was enough to throw a tremendous amount of material into a ring around the Earth, and then this ring condensed rather quickly to form the moon that we have today. So again, we can see this Mars-sized planetesimal comes in probably with its glancing type blow. As the two collide, the core of this impactor just sinks right to the center. But then you have this mantle material, which still has quite a bit of momentum, and that's launched into orbit around the Earth. There's enough angular momentum from that. This condenses and forms a ring, but eventually the particles in the ring come together and form the moon that we have today. So in summary, the moon is the largest terrestrial moon. Again, just to remind you, the terrestrial planets include Mercury, Venus, Earth, and Mars. Mars does have 2 moons, but again, these moons are more or less asteroids that were captured by Mars and didn't really form during the early part of the solar system in orbit. The moon has a very old surface covered with craters. Not only is it covered with craters, it's covered with a lot of this dust known as regolith. And the lunar highlands are old, and the mares aren't much younger, but they are younger than the highlands, and they're filled primarily with basalt. Okay, well that concludes our discussion of the Earth and Moon, and next time we will talk about the inner planets, the other inner planets, Mercury, Venus, and Mars. But it's important to remember some of the properties that we saw, especially with the Earth, because we're going to use these different properties to compare and contrast what we see in the other planets.